Hi there, welcome back to the second video of Homework 3 for Material Energy Balances. This is the coding part of Homework 3. The homework on your screen asks Part 2 to simulate the dynamics of this controlled three-tank system by solving the differential equations in Part 1 using SciPy integrate solve IVP. So that means what we're going to be doing is in Collaboratory, as I have up here. I have unnamed blank Collaboratory file open. We're going to be taking the equations that I wrote down from the part 1, inputting that into a function, adding the data points of the areas, specific heights, the proportionality constant, and the proportionality constant for the inflow. Inputting those into the file, into the code, into the function, and then using solve IVP to take that function and switch the heights around, and then plot it on a graph to show, all right, over time, how do these heights compare? So let's get started. So first and foremost, per usual, we're going to import numpy as np. We're going to be using numerical Python for most, if not all, of our math, besides for the solving at IVP. And we also, again, we're going to be using the subplots, so we're going to be wanting from plotly.io import make subplots. We also want to import plotly.io as PO. We want to make a default dark because we don't hurt our eyes. So that is plotly.template.default is equal to plotly dark. And now we want our SciPy optimized. So solve IVP. So from SciPy scientific Python, and this is SciPy integrate. So from SciPy.integrate import solve IVP. IVP, of course, stands for initial value problem. So we're going to be using that to solve the differential equations we came up with. So shift enter, hopefully the syntax on that is all right. We're connecting, we're running, initializing, nope. From plotly.io. Oh yeah, it's plotly.subplots. Oh, come on, fat fingers. Oh. There we go, syntax. Sorry, I was missing an S here. It was plotly.subplots, not plotly.io. Okay, now we're ready. So again, as I mentioned before, we're going to be making a function. So we're going to define a function that contains all of the information from the right-hand sides of our three equations for accumulation. So define RHS for right-hand sides, and then we need two variables. So let's go with, we need to start with T for time for solve IVP. Solve IVP needs to have time as your first variable, and then we're just going to call vec as a list of vectors, as a list of variables. So we're going to unpack vec. So as we know, H1, H2, H3 are all equal to vec. So these are our guesses. Our guesses for the height of tank 1 in the liquid in the height of tank 2, and the liquid in the height of tank 3. So we're going to be unpacking those and taking from our equations we want to input the flow rate from tank 1 to tank 2, from 2 to tank 3, the flow rate in, the flow rate out. So let's begin with Q of 1, 2, so Q12, flow rate from 1 to 2, is equal to, and I have it written here, numpy.sine of H1 minus H2 multiplied by, so numpy.sine does the same thing. It takes just the sign, the positive or negative value from it. So that one, it'll be times 1 or times negative 1 times alpha 1 times, then we need the np.abs of H1 minus the, so height of tank 1 minus height of tank 2. Enter. Okay. Now Q2, Q23, or the flow rate from tanks 2 to 3 is the same, so np.sine, numpy.sine, height of tank 2 minus height of liquid in tank 3, multiplied by alpha, or the coefficient, or the, what is it called? The proportionality constant of the proportionality constant times np dot abs numpy absolute value H2 minus H3. So again, height of liquid in tank 2, height of liquid in tank 3, then Q out, the flow rate out is equal to, as I wrote down earlier, alpha 3, the proportionality constant of tank 3, multiplied by H3. Ooh, I forgot 1/2, so I forgot to square root these, so multiplied by, not multiplied by, to the power of 0.5. And then same thing here, to the power of 0.5, close the parentheses, good. Okay, now that we have that fixed, the proportionality constant of tank 3 and the liquid in tank 3 times the height of the liquid in tank 3 to the power of 0.5. So the square root of that. Now we want Q in, the flow rate in, so Q in is equal to, as we put earlier, Kc, again, proportionality constant, multiplied by H3SP, actually I'm going to call it H3 underscore SP, so the set point of H of the height 3, that is the height that we want in tank 3, minus H3, so minus the height of the third, of the liquid in the third tank. And that's all we really need. We now what do we want to return? We want to manipulate the heights of, or the change in heights of the liquid. So the dH over dt from our initial, from our accumulation equation. So we're going to return multiple things. So for tank 1, dH1 over dt, or the derivative of the, or the change in the height of, for tank 1 is equal to negative Q12 divided by A1. So A1 being the cross-sectional area. Nope, that's not it. A1, enter. I just want to space that, not space that, enter that so it's more easily separated. And then T2 is equal to Q in, or the flow rate in, plus the flow rate from 1 to 2, minus the flow rate from 2 to 3, divided by the area of tank 2. And then finally, the rate of change in tank 3 is equal to, again, I need parentheses, flow rate from 2 to 3 minus the flow rate out. And again, divided by A3. Okay, shift enter. We have our function set up. So now we can input all of our necessary values. So we have here the cross-sectional areas. So A1, area of 1, area of 2, and not area of 2, A2 and area of 3 is equal to 0.5, 1, and 2, respectively. So 0.5, 1 dot, and 2 dot, just so it's not integers. That may mess things up if we're not careful, but now it shouldn't. And the initial fluid height level, so we're going to call that H naught per each tank of 0.5, 1, and 2, so they match up. So H naught 1, H naught of 2, and H naught of 3. So the initial heights of the liquid in tank 1, tank 2, and tank 3 is also equal to 0.5, 1, and 2, respectively. We need alpha, so yes. The proportionality constant between tanks 1 and 2 and 2 and 3 are 0.1 respectively. And the same proportionality constant, so alpha 1, alpha 2, and alpha 3 are all, what was it, 0.1? Yeah, 0.1. So alpha 1, alpha 2, and alpha 3 are all equal to 0.1, 0.1, and 0.1. We also have our Kc. So Kc, or proportionality constant for the flow rate in, is equal to, I believe it was 0.1. Yes, 0.1. And then what do we want for, or the set point for H2 for the height in tank 3 is equal to, I believe it was 4. Yes. All right. That should be everything we need. Shift Enter. I don't want this. Sorry, an unnecessary value or import made because of some autocorrect. So I want the backspaces. All right, should be all set up. So now we need to use solve IVP to take it, or to create a variable or function to manipulate the code, the heights, to effectively change it, to effectively run the problem and find a stable solution. So let's call this sol. It's a function, so sol equals solve IVP of what function do we need? We want RHS. We need the t-span. That's what we need. That's what I was forgetting. So we need we need a final time. So from initial time 0 to a final time tn, we're going to call tn 200 because we like that number. It's a nice round number. Shift Enter. From 0 to 200, to tn, so we can manipulate the time if we so choose, and then y0, y naught. We need for this one h naught 1, h naught 2, and h naught 3. So again the heights from the initial heights from tank 1, tank 2, and tank 3. We want a method. Method is equal to radau, and that's really just it's a slower method, but it's a very precise method, and I'm going to space here because otherwise we're going to start running out of room. Now, towards the end, we want a dense output. Dense output is equals true, and that should finish it. So we have that. Now we want just the we want the function from solve IVP of sol. So we have that. Now, if my syntax is correct, that should work. Shift Enter. Good. So now all we need to do is make a plot to plot this and look and see where are we ending up. So first of all, figure is equal to make subplots. Okay. Now we want to make a plot of the time, or linear amount of time from our starting point to our t-end that we used in the sol variable in solve IVP. So we're going to be using numpy.linspace, or linear space, from 0 to t-end, and we're going to call it 500 points because, again, nice round number, lots of points, make sure that there's no big jumps there. We wouldn't want a jump of any more than like 0.1 or something, or not 0.1 of any more than about 0.5. So getting it relatively we're getting multiple in 1 second is a good thing to do. We also need, for this, we're going to be using h1, h2, and h3. The values for it is equal to sol of tplot. So we're going to be running this sol function for tplot, the linearly spaced time, and giving and assigning values from those that array to these 3 variables. So now we're going to fig.add scatter. We want to add a scatter for the first height, so h1. We're going to, x is going to equal tplot, y is going to equal h1. We want the mode to be line, or lines, I think. That's syntax that may need to be changed. I think it's lines. And then name. Name is equal to, yes, name is equal to, we're just going to call it h1. And I can copy and paste that and simply just change some values in there. And once I change these values and enter it, fingers crossed, it should work. It should give us the value, the relationship between them. So fingers crossed, here we go. Shift enter, running. Hey, that looks nice. I like how that looks. So let's explain what's on the screen here. So we have the initial starting points at time equals 0. We have 2 for the height of in tank 3 is 2. The height in tank 2 is 1, and the height in tank 1 is 0.5. So if you reference back to our little drawings, immediately after as the things balance out, the liquid in tank 3 starts draining out. So you see that dip here where it's not being filled because it is flowing both out into the surroundings and into tank 2. So it drops down, and then somewhere in this area it starts rising back up as it's getting filled by tank 2, because tank 2 is bigger than tank. The height of the liquid in tank 2 is bigger than the height in tank 3. You notice how tank 1 quickly rises to meet tank 2 because it has a smaller cross-sectional area, which means it fills up quicker. So it quickly rises to meet it, and then once it meets it and it goes past it, it starts flowing back into tank 2 and drops. So at that point, they're effectively the same. So they rise slowly, equivalent to each other. Tank 3 has a much bigger cross-sectional area and thus volume of both tank 2 and tank 1. Specifically, tank 1 is much smaller. So its height it makes sense that its height is smaller than the others. It's holding the same volume of water, but it's at a lower height. It's also flowing out at a constant rate. So all of these are at equilibrium. They'll stay there, and then it's slowly flowing out as it's flowing in. So you notice that now there's an issue here. Our height, where is it? Qn. Our height here never reaches the set point for the third height, which is 4. We never reach it. We're not even close. But that's a separate issue at the very least. That's just an issue with the controller, as well as some other aspects of this specific simulation. At the very, very least, that answers part 2. We have effectively simulated the dynamics of the 3-tank system, and I'm going to save this as, which one is this? MEB Homework 3. Yes, MEB Homework 3, Material Energy Balance Homework 3. So we have our simulation here, and I'd be proud to present this anywhere if I ever get asked this question. Thank you very much for watching. I hope you have a wonderful day.